This is the third video on conditional probability-based theorem and independent events. In this video, we will go over independent events. Two events from the same sample space S are independent if and only if the probability of their intersection of them occurring together equals the product of their individual probabilities. Now, disjoint events are not independent, and the reason is that disjoint events have an intersection that is the empty set, and therefore their probability of their intersection is 0. But if their probabilities are non-zero, then it is not true that 0 will equal something that is non-zero. Now we want to show that if A and B are independent, then A and B complement are also independent. So I'm going to go back to my set theory rules and I will see what happens when I union and when I intersect those two sets. So I'm going to first apply for the union of the two sets the distributive property, and it's gonna come out to be A intersection B union B complement. And then I'm going to use the complement laws to say that B union B complement is the universal set. And then I'm going to use the identity law to say that A intersection U is A. For the next one, for the intersection of the two sets, I'm going to use the associative law to group them in a different way. A intersection A, intersection B, intersection B complement. And then I'm going to use idempotent to say that A intersection A is A, and complement laws to say that B intersection B complement is the empty set. And then I'm going to use the universal bound laws to say that A intersection empty set is the empty set. So I see that they are disjoint because their intersection is the empty set, and they are a partition of A because their union is A. Therefore, the probability of A intersection B union A intersection B complement will be the sum of those two probabilities, and it will equal the probability of A occurring. Therefore, the probability of A intersection B complement is the probability of A minus the probability of A intersection B. And because A and B are independent, the probability of their intersection is the product of those two probabilities, and I will factor out PA, probability of A. I will get 1 minus the probability of B, which is the probability of the B complement. And I showed that the probability of the intersection equals the product of the two probabilities, therefore the events are independent. An example of independent events is the following. We have a coin that is loaded, so the probability of heads is 0.6, and let's suppose that the coin is tossed twice. I want to find the probability of getting two heads. The events of two different tosses are independent, so we will assume that we can multiply the probabilities. So to get two heads, the probability will be 0.6 times 0.6, which is 0.36. To get one head, it is either I get a head first or I will get a head second. These are disjoint events, so I'm going to add the two probabilities. Probabilities of getting a head first is 0.6 and tail second 0.4. The probability of getting tails first 0.4 times the probability of getting heads second 0.6. 0.24 plus 0.24 equals 0.48. Probability of getting no heads is the probability of getting only tails. So 0.4 times 0.4, that will be 0.16. And the probability of getting at least one head is either one head plus two heads. So there are two ways of thinking about that. Probability of getting one head or of getting two heads. We can also think that it is the probability of the whole sample space 1 minus the probability of getting no heads. They both should come out to the same answer. So it is 0.36 plus 0.48, or it is also 1 minus 0.16. The answer for that should be 0.84. If the experiment is repeated many times, what is the expected value of the number of heads in two tosses? Again, remember that expected value is the number of heads in two tosses, 0, times the probability of getting 0 heads, plus the number of heads we could possibly get in two tosses, 1, times the probability of getting only 1, plus the number of heads we can get in two tosses, which is 2, times the probability of getting 2. The probability of getting 0 heads is 0.16 from this probability, plus the probability of getting 1 was 0.48, plus 2 times the probability of getting 2 heads was 0.36. If I add them, I get 0.48 plus 0.72, which comes out to 1.2. So the expected number of heads in two tosses is 1.2.